Okay, so yeah, we are back. Let me take your question. Before we continue. Okay, probably the person is not on the page yet. So let me move on, and then when you come in, you can ask the question. Now, so we have advantages and disadvantages of simulation. A simulation model can be used repeatedly to study the behavior, okay, of proposed designs and changes in operation policies without any additional cost. We can always study the behavior by changing so many things in the system. Now, simulation is usually less costly and safer than carrying out experiments and gathering data from real systems. This we know, okay? If you're sitting behind your computer and observing the behavior of a system, it's less costly than traveling all the way to go and observe the system, or even to build a real life system for demonstration. It's very expensive, okay? But you can either do that, you can easily do that using a simulation and change the parameters without any extra cost. Now, simulation models are easier to apply than analytic techniques, okay? That too, we know. So in very complicated systems, you can just apply simulation models, and they are friendly depending on how you program it, okay? So if you have visualization or animations attached to it, then you begin to see the behavior of the system very easy. The interpretation becomes very easy to analyze, okay? Yeah, I came across this, is it homeopathic simulators? Okay, sometimes you stand on a device and then it does its own scanning within a minute or two. It gives you a scan of your body system and tell you where there are challenges in your body, whether the heart is working well, there are problems with the eye, problems with the bone and everything. Okay, these are simulators. We also have some simulators used in the hospital to detect the heartbeats and etc. We have simulators for determining genetic combination and modification, okay? Yeah, they are very easy and you can interpret it based on the visualization, okay? Rather than just using, when I say analytic techniques, we mean solving them manually, okay? Maybe using a calculus method to find a solution to the system. It will only give you the answer without telling you, the behavior, the real life, or let me say real time behavior of the system. Simulation models do not have the restrictive assumptions that what analytic models often do, okay? They have assumptions though, okay, because they are also mathematical models, but we can always study even the behavior under certain circumstances, okay? So assumptions are a bit flexible. Okay, then he says in some cases, simulation is the only method that can be used to reach the solution of the system, which is very true. Okay, there are some situations, dynamic systems, which cannot be solved or cannot be studied using analytic methods. We have to fall on what? Numerical solutions or simulation models. Disadvantages: model building is not an exact science. So that's the first disadvantage, okay? As long as we are using a model, then we are not going to have 100% what? Accuracy. But it is an art for which it takes considerable effort and experience, okay, to acquire the necessary skills. So it will take some time. Yeah, you build, designing a traffic light system for the first time. You may leave out key relevant components as compared to somebody who has been working on that system for that particular traffic light system for some time now. Because he has experience, he might have conducted so many simulations and realized key components that should be taken into consideration on that particular road. Okay, so it takes a lot of experience. And at times you even building the model, okay? Building the model. It's not easy. If you even consider this physical simulators like the computer games, you consider your FIFA 2019, okay? It takes very experienced guys to put these things together, okay? But for you as a starter, you may start on a very small level, and then through experience and effort, you will gather the necessary skills. Simulation results may be difficult to interpret. Okay, some of the simulation results may not come with animations, or even if they come with animations like this sinusoidal graphs produced by the heartbeat simulators in the hospital. Okay, if you are not a trained medical personnel, you only see those graphs just going like that, but you really don't understand what they mean. Okay, simulation models and analysis can be time consuming and expensive. Yes, sometimes they can be time consuming, expensive, but you see, one thing about simulation modeling and analysis is once we have designed the model, that is it. Okay, once you've designed a model, you are done. Okay, the model for the system, you are done. So it's just a matter of changing parameters here and there. But when it comes to real life scenario, in building the model or the design, you may have to destroy the whole thing and rebuild, okay? So even though the simulation modeling can still be time consuming, it's far better than experimenting with real life. Then sometimes simulation is used where better techniques exist. So at times people may consider using simulation results when there are better options available, okay? Like analytic techniques. Then finally, we are saying that you should know that all these disadvantages can be overcome with what? Education and experience over time. Yeah. Then my brother who had a question for me, are you on the page now?
Yes, sir.
Okay, so let me take your question, move on.
So my question is based on simulation. Assuming you encountered an error during simulation, could that error be can that error be encountered in reality as well?
Yeah, I want to structure your question very well, because if you use error, then you are sounding more like you are still in the simulation model. That is, you are still doing verification. But what we are trying to say here is, assuming you encounter a system failure, assuming you encountered a system failure or a design failure, okay, whilst running your simulation outcomes, is it possible we will encounter that too in the real life? Yes.
Yes.
Yes, because those are an indication of the threshold of the system. This whole simulation process started when they were building the first modern plane. Okay, they tried physical modeling. They built the system over and over. and found on a very experienced pilot. And anytime they fly to a particular height, okay, it just turned upside down. So they had to run everything on the computer. And then when they checked at that same height on the computer, when the simulation outcomes, okay, came, you could see that the plane had just turned and was coming down. You could see the particles coming down in the output of the simulation, which gives an indication that given the parameters that were being inputted, no matter the experience of the pilot, the plane will still come down. So there was something they were not considering. And then once they changed the parameters, the flight angle and then the flight velocity, okay, the plane was able to move successfully. Until today, that flight angle and those flight velocity are being applied in the modern plane. You understand? So an indication of a failure, the reason why we run simulations is to check where the system is going to operate at its best and where it's going to fail. And then once we see the conditions and the failure, we put in measures to avoid that scenario. So it's a very fantastic question you asked. Good. Any other question?
Thank you, sir.
You're welcome. Any other question? Okay. So in the absence of any question, let me tackle the main types of model. Okay, and then we wrap up for today's class. So we talk about let me go back again before we come here. So I'll go back to the flow chart. So when we get to the flow chart from lecture 1, okay, you can see we have numerical solutions or simulation models. Can be classified into what? 3 main types. You can have static versus dynamic, deterministic versus stochastic, and then continuous versus discrete. So we want to look at them and then look at their explanations briefly. So the first classification here is we have dynamic and static models, okay? Now, when we talk about a dynamic model, then we are talking about a system which evolves, which changes. Okay, the state of the process changes over time. Okay, so cars arriving at a park or arrival rates at a bank, okay, they all change with what? With time. Okay, those are dynamic model, or the position of a car at a given time. Okay, it's a dynamic model. So if you are using the kinematic equations, those are dynamic model because they are time what? Homogeneous. They are time homogeneous. Okay, then we also have static models where, I mean, time is not a factor, like Monte Carlo what? Simulations, okay? Then the next classification is deterministic as against stochastic. When we say deterministic model, we are talking about models whose position or whose state value can be determined at any given point, okay? We can determine it, okay? That is why we say deterministic. In other words, it is not due to chance, we can know. So for example, if a car is moving, okay, if it is moving, we can tell that after 5 minutes at a certain velocity, this is the displacement or the distance is going to what? Cover. It's a deterministic what? Model. Okay. Then when it comes to stochastic modeling, we are talking about modeling processes or systems which come with what? A likelihood, a chance, okay? The probability of occurrence. So for example, there is a chance that a child born, the third child born by a parent will have blood group AA. You understand? The parents have blood groups A, and then the other person has B. Okay, but it is possible that one person is going to pick both BB and become blood group B. You understand? So there is a chance, there is a likelihood. It could be the first child, it could be the second child, it could be the third child. Okay, so it's just by chance. There is another system, could be weather pattern. It could happen that today it might rain or it might not rain. Those are all stochastic models. You understand? They happen with what? With chance. Queuing systems are also, another system with chance. Okay, it's possible somebody might arrive at the bank or nobody might be in the bank at all. It's likely there might be a queue and there might not be a queue. Okay, so all these things, okay, come into consideration. So there are more examples here on deterministic as against what? Stochastic models. Now, when you listen to the explanation I've given to you, then it means that one model can be both a model like determining, let's take, for example, this function here. Okay, considering the height of an object. Okay, at any given point in time is a deterministic model. At the same time, because it depends on time, it is also what? Time homogeneous, or what we call as a dynamic system. You understand? So the model is a deterministic model, and it is also what? A dynamic system, okay? Because the height changes with what? Time. So if you drop a particle or an object from the top of your roof, with time, the height is also going to what? Change, okay? So you can determine the height at any given point in time. At the same time, to the height, the value of the height is changing with what? With time. So it is both what? Deterministic and time homogeneous or dynamic. Let me put it that way. Okay. Then I think there are further examples on stochastic. I think I've explained that. Stochastic modeling, I've explained that to you. Then we've talked about, no, we've not talked about continuous and discrete models. When we talk about continuous models, we are talking about a system, okay, whose values occur continuously, okay? They are occurring continuously. So, for example, let me take an example on a discrete, then you see the difference. So when we talk about discrete, we are talking about change in the state of a system at only discrete point in time. So arrivals in the bank, okay, are based on what? Discrete arrivals, okay? So 1, 2, or 3 people entry. These are discrete counting numbers, okay? But the waiting time is continuous, okay? So if you want to model waiting time is a continuous process, which will require a continuous, okay, distribution model. But in the case of the arrival time, because it is discrete, you require what? A discrete, okay, model, a discrete stochastic model to predict arrival, okay? Good. So you can see that a model can be continuous, it can be stochastic, okay, and then it can be what? Dynamic, okay? So, for example, waiting in a queue is a continuous process, okay? And then it is also stochastic because you don't know when next you are going to move from the queue, okay? So it is a stochastic process. At the same time, too, the state of the system changes with time. So it is what? It is what? A time homogeneous, or what you refer to as a dynamic system. You understand? So one model can be classified. That's why we call it classifications. Either they are continuous or discrete, stochastic or deterministic, or we have dynamic or static system. Okay. Any question?
So I have one question.
Yes, go ahead.
One more question. So in the medical field,
Yes.
you know, when they want to test the how let's say they've manufactured a particular medicine for a cure.
Yeah.
Let's say corona.
Yeah.
And then they get this, let's say, these animals, or these animals to inject the medicines into them to know how it works.
Yeah.
Can you also tend that to be a simulation?
Yes, it's simulation.
Okay.
It's simulation. That's physical simulation. It's just like you developing your prototype.
Okay.
So they are creating a physical environment similar to reality. That is why they test on rats first. On some animals, they test it, simulation, try and error. So they test it on the animals and see whether it will work. Then they try another thing on humans. You see, that's why we are saying that physical simulations and experimenting with real life are very expensive. You see, they are very expensive because sometimes it takes the life of individuals, even though we have ethics when it comes to those biological experimentation too. Even if you are testing drug on an animal, you have to ensure that you keep the animal safe. The medical ethics to that. Good. Okay, any other question?
Yes, sir.
Yes.
Hello, sir.
Yeah, Gabriel. I think we lost
Yes,
Gabriel.
please. As the stick and the stochastic setting. So can you classify with the certainty, but with the stochastic, hello, sir.
Yes.
Hello.
Yes, I'm listening.
So I was asking if you can classify the deterministic model as a model with a high certainty, but with the stochastic, there's less certainty.
No. The moment you use the word certainty, you are talking about chance. Deterministic models do not occur with chance. It is known. So all you need is a parameter to determine it. So if I want to know the distance of a car, the distance traveled by a car, all I need is the speed and the time, because distance can be expressed in terms of what? The velocity and the time. You understand? So it is not a matter of certainty. When you use the word certainty, we are talking about certainty means sure, but when you talk about certainty, you are talking about likelihood, some aspects like you're having 90% or 99% assurance. No. Here we are saying that deterministic models can be, you can know it. You see, the word is you can know, you are sure that it will be there. But when it comes to stochastic, it will happen with a probability. It will happen with some chance. You understand?
Okay.
Yes,
sir.
Yeah,
Thanks, sir.
Yeah. More questions, please. Any more questions? Okay, the time is already gone, but I'll touch briefly on model development cycle so that I wrap up for today. Next week, we'll begin with probability theory. Now, I think we've talked about all of this, but let me just touch on it. Now, when we talk about the model development life cycle, it begins with defining the goal and the objective of the study. Or some book will say defining the problem you want to study, okay? Good. So, for example, a company has asked you to develop a model to resolve long queues at the airport, or a long queue at the bank, or at the hospital. Okay. Now, the objective is what? To reduce what? The queue at the hospital. Okay. That, so you clearly need to define the objective. Now, the next stage is to develop a conceptual model. Okay. Now, when it comes to queue at the hospital, which model does it follow? It's a queuing model. Okay. But what kind of queuing model is it? You understand? So we know it's a queuing model. What kind of queuing model is it? Then it means you are beaten down to what? To specified model. It's a specified model applies to the particular scenario you are dealing with. So in that hospital, there could be 2 doctors or 1 doctor. And for those 2 doctors, let's take the case of 2 doctors. For the 2 doctors, 1 doctor takes about 20 minutes to serve a patient, and the other takes about 30 minutes to serve the patient. Okay. Yeah. So you need to consider that into your model, the system model you are creating. You need to consider those parameters into the model. Okay. Then the next stage is to develop what? A computational model. The computational model is the implementation of that numerical, the model on the computer. Okay. So when we talk about computational model, we are talking about the simulation model, okay, on the computer. Then once you have developed that computational model, you need to verify. Anytime you run a program on a computer, you need to check to be sure that the program is what you are expecting. So you do some debugging. Some computer softwares, programming softwares are user-friendly. They are able to give you help aids. So wherever there is an error, it will tell you, go and check line so and so this particular statement. Okay. So you do verification. Then after you verify, you finally run validation. Validation takes place after you've run what? Simulation outcomes. Okay. But basically, these are the stages in a model development cycle. So if you want to construct a model, if you are modeling for your final thesis, okay, then once you start, you have your problem you are solving, you have the mathematical model you're going to make use. Probably you're designing a robot, okay, you have the problem you want the robot to solve. What is the mathematical procedures, the logical construction the robot has to follow to work? Okay, now you talk about the specification. Under what condition is this robot going to work? What is the weight and all those things associated to that robot for it to function? Okay, what, all these things. Then you implement it on your computer. After that, you need to verify whether it's really going to function. Then once it functions, you have to run simulations. It's a prototype, but you need to run simulations. Okay, at times you meet students who have developed robots for measuring the dimensions of a plot of land, or for measuring something, for estimating something. Okay, then during their final viva, they show up with their robots, and then you realize that the robot does not function. Why? Because there are certain conditions which were not factored, okay, whilst running the model of the process. Conditions like the sunlight, okay, calibration of the sunlight, okay, power and all those things. All these things can affect your system. Okay, so the robot comes and you input parameters, move 1 meter, and the robot is moving 2.5 meters. We've experienced that. So you need to run a number of simulations. It is through the simulations you realize that under this condition, this robot is going to work this way. So what do? Under this condition, this is what is going to happen. So that your robot, okay, is able to work as expected in real life conditions. Okay, so on that note, I'll wrap up. There are further explanations, but because of time, I've explained everything to you in a brief. Okay, so when we finish the lecture, just go through on your own at home and consider all the samples that are given the material. Next week, we'll be looking at probability theory, where we introduce ourselves to a lot of stochastic modeling techniques, okay, which will be used in further prediction and subsequent lectures. Yeah, so I'll wrap up my lecture here. If you have any questions, you can ask for me to address before we go. Any questions? Okay, so it appears we are all okay. I'm not getting any questions from anyone. So we'll wrap up today's lecture here. I'll be posting them on YouTube, so watch out for the videos and follow at. Okay. So on that note, I wish you the best for your weekend. Okay. See you all next week. Bye-bye.
Bye. Thank you.
Thank you, sir. Bye.